Okay. You're on mute. Good. Okay. So it's my pleasure to introduce Stephanie Milani, who's finishing her PhD at CMU with defy. Steph has a number of interesting recognitions, including Best Paper Awards at a couple of machine learning workshops, and honors with names like Future Leader and The Next 10 and Rising Star and stuff like that. But the reason I am looking forward to her talk is that she has a TA award, so we know she's a good teacher, and we can sit back and enjoy the ride. I was thinking when looking again at Steph's portfolio about the ending of her, which, spoiler alert, plug your ears if you haven't seen it, the AIs go off because they'd rather talk to each other than to the people, and Steph is trying to make sure that they will, I don't know if they will want to talk to the people, but at least they'll be able to. So she works on topics like keeping in the loop and has a tutorial on explainable reinforcement learning. I guess we'll figure in today's talk. Let's welcome Steph.
Thank you guys for the introduction. Thanks for coming. So yeah, I'm excited to present my research today on rethinking AI agents from the perspective of human subject-based system learning. Let's see if this clicker will work. Cool. So although I used to live in Baltimore, I actually didn't get the opportunity to visit Hopkins. So whenever I was invited to campus, I was really excited to visit the system. So I asked about the team to help me plan my travel. And this is the response I got. So it's very encouraging and supportive, but I already know how to do this kind of high level. So that wasn't quite what I was looking for. Instead, I was aiming for something more like this. Search defines a direct flow, and it accommodated my preferences and my airport, and then asked me whether I wanted to book it or not. And I think this illustrates this kind of growing trend in the AI landscape where we're moving from strictly conversation systems to also agentic systems that can take action on our behalf. And beyond this large language models, there are different types of statements about that's what I'm really focused on. So beyond that, we can see AI agents that are making sequential decisions and things like that. So you can see this in robotics, and you can see AI agents being developed for education and so on. And importantly, this means that AI agents are acting in these human environments. So then a key question that arises is how to actually build agents that can operate well with people. I think that there's chat. The audio is garbled. Okay, yes, thank you, Charlie. I'll try to speak up a little bit. Is this a bit better?
We're saying yes.
Yes, thank you.
Okay, perfect. I'll try to project a bit more. Thanks. Cool. All right. So first I'll pause to provide a definition of AI agents. And this is a very broad topic, so I'll just let you know what I'm talking about when I refer to agents. So in particular, I'm using the Russell and Norberg definition, which is just an agent is something that receives the input through sensors. So that can be in embodied robotics, that can also be in, let's say, web agents, and then acts upon that. And in particular, when we think about bringing AI agents to these more human settings, there are a few key challenges that emerge. I think there's plenty more, but I'm just going to focus on three that I'm really focused on in my work. So first, we might want to be able to understand the decision-making process of these agents. So in this particular example, this is this instance where Tesla drivers were reporting something called depth of braking, which is just that the car would brake for no real discernible reason. And what happened was that people ended up constructing a lot of folklore about what was going on. So people would say, well, it's just a natural reaction to a post-sleep change. And then others would think that there was a sensor failure where shadows were as obstacles. This led to a lot of unhappiness with the product and also mistrust. But instead, I think we want something that's more of a transparent decision where we can foster appropriate trust, especially in these high-stakes settings where safe deployment is really crucial. So maybe it looks something more like this, where we get a more accurate explanation of the actions of a self-driving agent. And it also can help developers debug these agents if something were to go wrong. Second, if we have all of these different possible use cases for agents, it's likely infeasible to be able to have this massive agentic model that can do all of these possible goals. And so we need a way to actually just determine what goals these agents should optimize for these particular use cases. And so, for example, this medical AI was not really optimized for the doctor's workflows, and so it ended up being abandoned. Instead, we want to more thoughtfully design these AI agents to actually accommodate the workflows of people and align with their goals. So here, instead, we want something that enables better patient care. And then third, I want to be able to learn from people in more naturalistic ways. So rather than just manually pressing these buttons, it would be nice to be able to communicate directly with the agent, let's say in natural language, and how to accommodate our preferences. So maybe you're not a morning person and you want your meeting scheduled for so these challenges all share this common theme, which is AI agents must operate effectively in these human environments through interaction. And so human-centered reinforcement learning takes human-centered AI and reinforcement learning to prioritize the needs and goals of people and the human factors throughout the design process of these agents. And this is all with the goal of addressing these more human-centered and world challenges. So the majority of my work is focused on these four areas. So interpretable or transparent decision-making, understanding or specifying the goals for agents to optimize for, building algorithms and benchmarks for agents to learn from people, and finally developing reinforcement learning agents that can learn and assemble. But in this talk, I'm just going to focus on a subset of these, so interpretable decision-making, understanding and specifying goals, and learning from people. So in the first part, we'll go a bit deeper. So I'll show how rethinking interpretability from this human-centered reinforcement learning perspective can enable this opportunity for new algorithm development. In the second part, we'll think about how we actually arrive at the goals that we want these agents to optimize through a use case in mental health. And here I'll show how human-centered design can offer a path to actually create these goals. And then third, we're going to look at how we can actually enable these agents to learn more realistic tasks. So we call these fuzzy tasks where it might be hard to specify them. And in particular, I'm going to highlight our benchmark for agents to learn easily. Before I do that, I'll give a little bit of a tutorial on reinforcement learning, just in case there's people who aren't familiar. So the idea is you have an agent and an environment. The agent takes actions in the environment at each time step. The environment in return gives it a state and also a reward. So the state lets the agent know what setting it's in. You can think of it as like a game frame. And then the reward lets the agent know how well it's doing at a task. And the agent takes actions following a policy pi, which essentially just maps each state to a probability distribution over actions. And then the goal is to actually maximize the discounted future reward. So if we take the trajectory tau, which is a series of data tuples, and we apply a discount factor, which basically tells you whether to weigh the rewards in the future more or less, and we sum that up, that's what we want to maximize. And this is what makes reinforcement learning different from areas like classification, where instead of just making like a myopic or 3D decision, we want to optimize the behavior over time. And importantly, this is good for our setting because we have already established that AI agents are going to be making sequences of decisions in these environments. So this makes reinforcement learning particularly well suited. Great, so now let's go into the first part. So I mentioned that these AI agents are making decisions following these policies, right? And to do that, we often need these policies to be these complex neural networks that map from these states to actions. So here's an example in the self-driving setting. So we might have this complex image input state. It goes through a neural network policy, and then the agent gets an action recommendation. But instead, I think it would be nice if we could actually get these the input as a function of human understandable concepts. So here you can see that the agent is taking actions based on the pedestrian sign, also there being a pedestrian in the walkway, and also that there's a stopped vehicle in front of it, and those are influencing the decision to actually stop. And we can actually do this through this technique called concept bottleneck models. This has mostly been done in a classification setting, but the idea is that we can insert a bottleneck into the network to also have this auxiliary task of predicting these concepts. Now I'll go through that in a little bit more detail. But I'll just highlight a couple benefits of this. So in addition to asking these sort of why questions, like why did you stop, you can also ask counterfactuals, such as what would you have done had there not been a car stopped in front of you? And here, maybe the self-driving agent says that, well, they still would have stopped because there was still a pedestrian in the way. Okay. And so I mentioned that this is mostly done in the classification setting, but I'll show that we actually can rethink this from the perspective of human-centered reinforcement learning to identify these algorithmic challenges. So this is what the process looks like. We go from the kind of concept learning part, mapping from states to concepts. Then there's this behavior learning part, from concepts to actions. So to train these, we'll do two different techniques. So for this part, we'll use supervised learning to get from the states to the concepts. And for behavior learning, we can just apply any RL algorithm of our choice and it will work very well. Cool. So what's the challenge here? Well, in reinforcement learning, we have an agent that's collecting its own data. It's not like in the supervised learning setting, right? So what that means is that at each state, we ask a human what concepts are present, and then the human provides the ground truth, and then we use that for training. But reinforcement learning is quite data hungry. And so that means that it can require millions to billions of concept labels from a human in the loop annotator for training, which is just quite infeasible for a human to actually get. And so in this work, we ask the question of, can we do better? Can we actually improve the efficiency of this algorithm in terms of the concept labeling efficiency? So maybe we can first kind of try to come up with a baseline. So this is just a sequential baseline. So the idea is that, let's say we have this budget of B data points that we want to be able to collect. We can do the following. We just initialize our policy, deploy in the environment for B time steps, and then we can ask a human to label all of those data points. Then we can just learn those concepts and then train the decision-making function on top of that. What is the challenge here? Well, the distribution under a random policy and an exit policy is going to differ greatly, right? So if we just do this sequential process, and I'll show the implementation of this, we actually struggle to achieve high performance. So here, the brown is the kind of previous work in the reinforcement learning setting that assumes unlimited access to concepts. And then the blue is this baseline that is implemented. So you can see that the gap in reward is quite large. And this is a problem because in addition to being interpretable, we also want the agent to do the task well. Okay.
Quick question.
Yes.
Since you're showing results now, I want to make sure I know what the system is doing. Is it bottlenecked by the concepts?
Yes. So both of these have this concept bottleneck portion included. And do you mean in terms of the reward?
Well, if you go back to the previous slide 16, I wasn't quite sure how to interpret this diagram. So this seemed to show that the whole state goes into a network along with the human annotation. So it still has access to the whole state. I didn't see the bottleneck.
Oh, I see. So what's happening for decision making is that the agent is only getting as input the concepts. So
I see. So C is predicted concepts.
Yes.
And when X, Y is feeding in, that's as a training signal.
Yes, that's
only a training signal. Okay,
yes,
got it. Thanks.
yes, exactly. You can have these side channels of maybe different, maybe uninterpretable kind of inputs, but we chose to strictly make decision making a function of the concepts.
Okay, and well, out of curiosity, what is the network on the right, the purple one that just looks at concepts? Like what kind of network is it?
Oh, just like a standard like feed-forward network.
Yeah, okay, so you didn't use decision forest or something like that?
No, but that could be interesting to explore.
Because it's a small number of features, right?
Yes, so it's a small number of features, so you can potentially just have it be like, I don't know, some sort of like softmax over the concepts to make it a simpler decision function. In RL, it's a little bit tricky because sometimes you actually have a more complex decision-making process that you want to represent. But yeah, so currently this is maybe, it's a very small neural network, maybe like 2 or 3 layers. It's not very large. Any other questions? Yes.
Thank you. How to define the vocabulary of the concept? Is a human predefined or task specific?
Oh yeah, that's a great point. So I think that there's a few ways to do it. So for the reinforcement learning setting, because we're using the concepts as sort of a substitute for a state, you want them to potentially have the Markov property. So you might want to define the concepts such that if you take an action based on that, then you can actually like know how to behave well in that environment. But I think there's an exciting opportunity to potentially use like, let's say, vision language models or LLMs in general to explore the space of concepts first, and then maybe narrow them down. Thank you for the question. Cool. Okay, so this is the baseline. It doesn't do well. And this is because of this particular challenge. So this is the sequential training aspect of the baseline. So what I mean by this is that we do the concept learning portion first, which means that we do something like cross-entropy loss for these supervised learning signals, or we can use something like MSC in the case of continuous concept. And then we go and next go to the behavior learning part. Means based on these concepts that we've learned, we learn behavior. And this is just using like, let's say, standard PPO loss. And here, what we do is we introduce this iterative training process where now we interleave freezing both portions of the network to gradually bring the constant distribution closer and closer to what is more on policy. So that's the first part of the algorithm. The second part of the algorithm is that one challenge here is that states of different concepts might be temporally correlated, and as a result, they're kind of less diverse. So keep in mind, we're trying to construct this data set from which we want to query a human. So we might want to actually make our data set more diverse, so that we can actually get a better coverage of states. And so I'll just give an example here, but I think it's pretty intuitive, which is, let's say you have 5 data points that is your budget. Now if you want to, so what would look like is that maybe the agent is deployed, it takes this particular path, and then this is your data set. So that's with this no decorrelation procedure. So we just say, what if we just add a rejection percent? It's a very simple idea. And so this can result in something that looks more like this, where the agent gets better coverage of the speeds and therefore gets a more distributed data set for learning. And this can also be illustrated through like a standard RL environment, which is carpool. So if you were to do this approach, if you're trying to balance a poll, you might only get to here. But if you do our approach, you might be able to actually get the full coverage of the states that you would encounter in training. And then third, the challenge is that some states might be less informative. So we need to know when we actually want to ask a human for labels. So we do this technique called disagreement-based active learning, where the idea is that we train additional concept models with random initialization so that they are different, but using the same data that we've collected over time. And now the insight here is that if we ask each of the models to predict the concept labels, if those labels all agree, then that's not very interesting. We've already maybe learned what the concept is there. So instead, we characterize the states that have the most disagreement, and we use those as our acquisition function for actually querying the human for these labels. And then the human would provide this label. And so altogether, this is our algorithm. This is called Licorice. It's exciting work that was recently published in iClear. And so I'll show the results of actually using this algorithm on a variety of domains. So first, we verify that our algorithm can achieve optimal or near optimal performance on these environments. So here, higher is better. The pink is ours, brown is the previous work that has unlimited human labels, and blue is that baseline that we looked at that didn't do so well. And you can see here that across all of these domains, our algorithm achieves basically the same performance as the one that uses unlimited human labels. Cool, so it's performant. Now let's look at the number of human labels that are needed. So here, lower is better. So I'll just compare ours versus the unlimited human label algorithm. And this is on a log scale. And so we can also see that across these domains, our algorithm requires substantially fewer human labels to actually achieve that high performance. And so from this, we've really seen how we've tackled this kind of human-centered challenge of limited human labels in this process. And naturally, since our kind of goal is to alleviate the human annotation burden, we say, what if we use these powerful vision language models instead of human annotators? So the process looks like this, where instead of providing this kind of natural input to a human, you'll need to label what you see in this image, then we actually just provide it to a vision language model, and then we use that as ground truth for training the state to concept mappings, the concept learning portion. And you can see here, so here higher is better, this is just the performance. We can see that there's still a significant gap in terms of performance when you use these vision models as annotators. And I think this is a really exciting opportunity to improve.
Yeah, so the purple legend, should that be Ligorous minus human plus GPT-4?
Yes.
Okay, thanks.
Exactly. So in particular, I think we can maybe leverage these learning to defer algorithms, so you can take advantage of the complementarity of these tasks. And then also maybe we can do something like improve the actual prompt selection here that is designed for this particular task. So I think there's opportunity to look at the human complementarity aspect, and then also improve the capabilities of these data language models to take advantage of their implicit knowledge. And then just a quick note is that the decision-making portion, so this portion of the network requires some particular structure. We can apply our previous work, which is in a simulated and multi-agent setting, which essentially transforms neural network policies into interpretable structures while still maintaining the performance, so that a human can verify the structure before it's deployed. Cool. So that's this part. So we've shown how we can efficiently learn performant and interpretable concept-based policies. And we've also shown how rethinking interpretability through this human-centered reinforcement learning perspective enables us to come up with new algorithm designs, and also there are new algorithmic challenges and opportunities that bring these implementations closer to the real world. Maybe I can pause for any questions.
Question. So here the concepts on the state space, right?
Yes.
So how do you think about like a concept in the real world space, or like I feel like that's also very important for RL applications.
For real world space,
Like the real world space. Like
real world,
yeah.
I see. Yes, I know that there's some work by Dean Kim that looks at concept-based reward interpretability, and I totally agree with that. I think that that's another really interesting direction, is how do you actually get the reward in a kind of factored manner, so that you actually know which component corresponds to the decision.
I had a question, and maybe I hate to interrupt you, but take your bus stopping example. The presence of a pedestrian in the scene isn't important. It's an action that the pedestrian is moving in a way that that could be a problem. So, to what extent, it seems to me that puts a much greater burden on your vision-based AI because it not only has to learn labels in a picture, but also needs to learn actions. Do you see that as a significant problem?
Oh, interesting. So if I make sure I understand the question, the point is that the kind of decision-making based on what the human is doing is also something you might need to explicitly model in the process, because you might need to actually, let's say, predict what the person is going to
It's
do.
not only what the human for whom the agent is acting is doing, it's what else is dynamically happening in the environment that would affect the human's decision.
Yeah, I think there's a lot of really interesting opportunities there. So one thing is that in reinforcement learning, if you have, when you're trying to get this more Jovian representation of your state, you can just encode the kind of previous frames to basically simulate the dynamics. You could also do something like try to explicitly learn what's called a world model, right? So that you actually get a predictive representation of the world, and that could involve predicting.
Well, yeah, but that's predicting the effect of what the agent is doing.
Sure, but you can also predict, you can also maintain an explicit human model and incorporate that into your predictive representation as well, right?
Well, there could be a lot of things. I mean, you have another car is moving rapidly across your path. I mean, the point is that human decisions in the physical world are not based on a static perception. They're based on a perception of what's there together with a perception of dynamics.
Yes, I totally agree with this. I think you're right, there's a lot of possible opportunities to bring this even closer to a real world.
The question then is it scalable?
Mhm. Yeah, so
That's a long question. I'm sorry for interrupting you. I usually get annoyed when other people have a long middle of a talk.
oh no, you're totally fine. I think this is a good question. I think my quick answer, and then maybe I'll go to the next part, is that I think that we started working on making this more scalable by addressing this human labeling challenge. And I totally agree with you that there's these additional components that we'll need to kind of bring it closer to real world deployment. So I will say I don't know if it's scalable in the sense of dynamics modeling, et cetera, but I think it's a really exciting opportunity to actually move this into a more real world setting. Thank you for your questions. So now let's go to the next part, which is understanding and specifying goals for these agents to optimize. Okay, so in the previous part, we've assumed the following. We've assumed that for all of those tasks, so I didn't go into the tasks very in much detail, but we've assumed that we know what the agents should be able to do, right? So we've done this by encoding it through a reward function. So for example, we might have the reward or the task be to navigate to a goal. But as I mentioned before, we might not need to have this massive agentic model that can span all of these possible tasks. So for example, those are AI tax agents also need to be a therapist, not. And so if we do this more domain-specific approach, this kind of unlocks these very specific goals within these domains that requires understanding the real-world context in order to establish appropriate goals for those domains. And so in my work in this section, we're going to look at this application of mental health. So in particular, I think that AI agents could make a difference in mental health for the following reasons. So mental health is a global health challenge where 1 in 8 people globally are living with mental health conditions, according to the WHO. And once these people actually can overcome the barriers that they already face in seeking help, they often face an obstacle, which is therapists are often overbooked. So as a result, there's this need to not only train more mental health professionals to accommodate this growing need, but also support current professionals. And so I think that AI agents can be useful in both of these settings. But in particular, we're going to talk about how we can use AI agents to train mental health professionals. And so specifically to kind of figure out what ways that these AI agents can actually help train, we use this process called human-centered design. I think the HCI people in the room will, maybe this will be a little bit redundant, but the idea is that we can actually just talk to people to establish what appropriate goals are for this particular domain. So for this work, I actually sat down with 5 mental health trainees. So these were social work students, and then 7 experts who had varying experience working with patients. And I wanted to understand how AI agents could potentially be useful for training mental health professionals. And this ended up with around 7 hours of transcripts and interviews. And from that, we could really distill 3 key findings. So first, all of the mental health professionals found that their training did not prepare them for speaking with real patients. And in particular, they found that it was very difficult to just move from going through textbooks or role playing with their peers to real world settings. And they also were very excited about the opportunity to use AI as a training tool, which I found to be kind of surprising because many people are concerned about AI taking over their jobs, but actually being used in an educational supportive setting was very exciting.
It's okay if they take over the patient's jobs.
Well, we're not trying to take over the patient's jobs.
The AIs can have all the mental health problems.
Yes, exactly. And additionally, we found that what came up oftentimes was that the therapist mentioned that there were different conversational styles of patients. So anything where we might have wanted to simulate patients would need to have different conversational styles to reflect real patients. And that means that we have now a few goals. So we want to create this AI-powered patient simulator, and we also wanted to have fidelity to real patients, and we wanted to be effective for training. So what we did is we built this solution grounded in these psychological principles and also involving these conversational styles that were identified in this. So what does this look like? Well, we first take what's called a cognitive model, and I'll briefly explain that later. We develop a data set of these with our mental health professional co-authors, and then we use that to program the LLM along with different conversational styles. We basically tell the LLM how to act like a patient who's maybe more reserved. And then we have a simulated patient. The trainee interacts with the simulated patient. And at the end, we essentially formulate a prediction task for the trainee, where the trainee tries to predict the underlying ground truth cognitive model that was used to program the LLM. So for the cognitive model, this looks something like this, where the agent has some sort of core belief or a coping strategy. And so at the end, the trainee tries to predict what these are from the natural language interaction with the patient. And this is a kind of core competency for therapist training. So in a real training session or a real session with a patient, the therapist would maybe maintain this cognitive model through the multiple sessions with that patient. This is just an example of the different conversational styles. So this is reserved, this is verbose. You don't have to read it, but you can just see the difference in the length. And maybe one of these resonates more with you, conversational styles. And so now we move to evaluation. So how do we actually evaluate this? Well, we again turn to people as evaluators. So again, we evaluate 20 experts and 13 trainees. I'll just show the expert results. So we compare our approach to GPT-4, where here, darker blue is ours is better, red is theirs is better. And we also ask them about training effectiveness and also realism to real patients. So overwhelmingly, the experts say that ours is better along these 2 factors. And we also ask them to compare against the more traditional training tools, such as interacting with peers. And again, the experts remarked that ours was significantly more realistic and had a higher potential to be effective for training than these more traditional approaches. And finally, we confirmed that the experts specifically preferred to practice these conversational styles. So they unanimously preferred it and remarked that the conversational styles are indeed more reflective of real problems. So I'm really excited about the impact of this work. So in addition to more work in this kind of space of simulating humans as a training tool, we can see that there's a lot of work being built in the space. There's also lots of opportunities to improve. And I was also really happy to see that CMU's School of Computer Science News featured us on the home page. And additionally, I saw that there is a non-English tutorial of our work, which I think goes to show that globally, people are very interested in this challenge of addressing these mental health. Great. So I've shown how we can actually use this human-centered design process to develop humans throughout the evaluation and the design process as a way to specify these particular goals for agents to achieve. And we've seen this in this case study of mental health. And so next, I'll talk about our evaluating them. So we have these maybe potentially fuzzy goals. How do we actually think? And in particular, we want to be able to reach a return in this because we want to reinforcement learning. So you might have noticed in the previous part, there's no reinforcement learning at all. And that's because there are a few challenges that emerge in the real world setting that make it difficult to apply for all. So I'll explain what I mean. So I'll highlight it through first a benchmark that we previously developed, and then I'll talk about and contrast that with real world settings. So we previously established this thing called the Diamond Challenge, which is in Minecraft. It's a very popular video game. And the idea is there are many possible goals using Minecraft, but one crucial thing that you need to do is to find a diamond. And that enables you to do things like build better armor, fight off monsters. And the thing to know is just that although this is a very complex challenge, it has some properties that are sticky. It's a very clear reward signal. You can say agent gets 1 if it gets a diamond, 0 if not. And additionally, you can use the game state to just check whether the agent has it in their inventory. But in real world applications, these goals are not as well defined. And also they might actually be hard to check, right? So we might need to actually, in these real world settings, such as cleaning a house, we might actually need to have a human tell us when it's done. And so in this work, we actually look at these particular tasks that have what we call this fuzzy properties. So they're kind of underspecified, and that human feedback kind of defines the objective. And so in particular, we need good benchmarks and evaluation to actually make progress toward this task. And so I'll just maybe briefly talk about how this is done, and then we can look at what we did. So the typical setup is that you take some existing benchmark, you train an agent with some potentially synthetic feedback, then you take the reward function from this benchmark, evaluate the agent. Good. Simplifies evaluation, but it requires the specification of the reward to begin with. And when we think about learning from human feedback, we can think about it like we have a bunch of potentially plausible goals, plausible ways that we could clean a house, and we want to actually select among those goals. But in these kind of benchmarks, the only thing that an agent can really do here is move forward or fail. And so if we're trying to evaluate this kind of goal selection process, we want to have a wide set of reasonable goals in the environment. So this brings us to our benchmark, which is called mineral basalt. So this is the first embodied reinforcement learning benchmark where we actually don't have a concrete reward function. So instead, there's a natural language specification of the task. And in particular, the challenge here was to, so we held it at NeurIPS for 2 years of competition. And the challenge here was for people to train or fine tune an AI agent using human feedback. So this is the kind of pipeline. We gave them a task description. We partner with OpenAI to provide them with these pre-trained Minecraft-based foundation models. They trained their agents using human feedback of their choice. And then for evaluation, we did pairwise human judgments of agents and humans performing these tasks. And we stopped having the competition, but we really wanted to promote the development of these algorithms. So we released 2 data sets. One was demonstration, it's around 14,000 videos of humans completing these tasks. And the other was the evaluation from the competition. So this is 3,000 around pairwise comparisons of humans and agents completing these tasks. So for example, here it's like which of the players actually created the waterfall, and they can select left, right, or none of the above, or both. And so this is the first kind of multi-objective comparison data set to my knowledge for agents. So in addition to asking about the task completion, we also recognize that this evaluation is fuzzy because there are other factors that are influencing decision-making, not just task completion. So we also asked about human likeness, other location, and so on. And so if we factor this out, this results in almost 28,000 total head-to-head comparisons. And so if we actually look at the kind of performance of humans versus AI agents, the spoiler is that people still outperform AI agents along all factors. So here, the pink and the kind of brownish color are the humans, and then the best performing AI agent is going to be this orange one. And we can see that here, higher is better. We can see that, for example, for the task performance, they still outperform the agent, but then along other factors, there's a much bigger gap. So there's a lot of improvement still to be done. And this is just for one of these tasks, probably arguably the simplest one. And so I'm also really excited about the impact of this pretty big part. So we had the Diamond Challenge competition for 3 years at NERSC, and it attracted a lot of interest from, for example, industries. There are quite a lot of algorithms being designed for the benchmark, and also related benchmarks being built upon it. And I was also really excited to see it being used in the classroom setting. So in particular, I saw that USC and also Cornell were using this in their lesson plans. And it was also featured in Hugging Face's deep reinforcement learning course. And then for Basalt, we had it for fewer years, only 2, as a competition. But I'm also really excited about the impact of this work. So in addition, I saw that at Boston University in their deep learning course, which is a project-based course, students actually tackled this challenge in their project. But yeah, that was really exciting to see that they had competed in the competition. And so what we've seen here is that with learning from people, AI agents still struggle with these embodied and kind of fuzzy or hard to specify tasks. And so rethinking from this human-centered reinforcement learning perspective can really highlight current gaps in evaluation and also in terms of capabilities of agents. So that's the work that I wanted to present today. I'll now go into future work, but I don't know if there are any questions that I can answer before moving into future work.
Maybe I can ask kind of an open-ended question about your next to last bullet point here.
Yes.
Yeah, so you mentioned education.
Mhm.
So education has always seemed to me to be it's a reinforcement learning problem, but with unobserved reward, I think. So you can't directly measure the learning of the student. You can only take actions that reveal something about whether the student was learning.
Yes.
So how well does that fit with how well does your current thinking address those kinds of problems?
Yeah, so I think it's a really exciting opportunity. So in my earlier work in my PhD, we actually looked at reinforcement learning-based intelligent tutoring systems.
Right.
And I think the main bottleneck there was really what you're saying, which is that we can simulate students, but we don't actually know whether they're learning. So that was the kind of key bottleneck. And I think I'd be really excited to actually evaluate these algorithms with real students. And I think you can do things like give them exams, give them quizzes, and use it as sort of a proxy signal for learning in pre and post test conditions. Does that answer your question?
Well, let's take it offline.
Okay, cool. Yeah, I think it's a really exciting area of work, so I'd be interested in pursuing it. Great. So for future work, let's give a broad overview. So in my work, I've looked at reinforcement learning, foundation models, and human-centered, and in this case, inspired AI. And moving forward, there are kind of 3 main directions that I'm particularly interested in working. So the first is this idea of more personalized and naturalistic human AI agent interactions. So in particular, I think it'd be nice if I could actually specify my goal in natural language, have the agent ask follow-up clarifying questions, maybe identify its own sort of uncertainty about which particular aspects it's uncertain about, and then I can then follow up and then provide my own preference, which then updates the agent's belief about my own preferences, and I can act in that way accordingly. And then also, I think it's really interesting to integrate these different signals that we might get in more naturalistic human AI interactions in more principled way. Second, in the interpretability work, we've mostly been talking about interpretability from the perspective of we have an agent, we get it into a structure where we verify it, and then we deploy it. But instead, I think it would also be really interesting to think about different modalities of human AI interaction and design interpretable algorithms accordingly. So for example, here, maybe we have an AI agent that can achieve superhuman performance on a task. And we can develop then techniques to enable a human to interrogate the decision-making process, maybe interrogate the internal representations of the network. And then we can use that to improve human understanding and decision-making. And finally, I'm also very interested in this kind of human-centered AI to support real-world use cases such as mental health. So in the simulated patient setting, there's a lot of opportunities to improve. So first, we only looked at this kind of single interaction setting, but actually this occurs over time, so we don't want to do that. Also, there are various training competencies for the therapists that we might want to capture. So in addition to just constructing that cognitive model, there are other competencies like building rapport with the patient that we might want to also capture in this. And additionally, both the agent and the human are going to have evolving preferences. So the trainee should have different preferences in terms of how they actually apply therapy because they're learning. And then the patient should also have preferences because hopefully the training is helping them to be able to improve on their mental health. And so I'd be very excited to look at this direction. And then also, I think there are other applications that are really exciting, such as using voice assistants, what are the kind of human-centered challenges that we manage here, also health, and education. And so that's all. Thank you for listening, and I'd love to take any questions.
Yeah, very interesting. If there are not questions in the audience, can I just ask, well, first a quick observation, the therapist stuff in a way goes way back to Ken Colby, although somewhat different here. But it seems like where you're likely to have the most success with these agents for the foreseeable future is going to be operating mostly at a symbolic level, where in terms of conversations or, you know, find me the best way to get to Baltimore or whatever. When your earlier, your first section, you were asking about, you had also examples from the physical world where things get more complicated. How do you see that progressing?
That's a good question. So maybe this also speaks to your questions earlier about kind of scaling up challenges as well. Mm-hmm. So I think for me, I'd be really excited. So I don't have expertise in robotics, but I would be really excited to collaborate with roboticists to see how we could actually bring these agents into the real world. So maybe we have some language or some kind of knowledge that's pre-trained into these large language models, and we need a way to do like language grounding in the real environment. And then we can look at trying to efficiently learn how to ground these internal language representations to the real world setting. I think that'd be potentially an interesting direction to pursue, among other things.
Okay, well, thank you. I'm not on your schedule today, but if we can exchange some email, maybe I could find a time to talk to you about that.
Yes, I'd love to. Let's set that up.
Okay, maybe your host can do something. Okay.
Yes, thank you, Vincent.
Yeah, very interesting talk.
Thank you.
So also a question on the mental health example. Just first a clarifying question. So if I understood correctly, the intervention, you're sort of comparing intervention to control, where the control is like this GPT-4 baseline,
Yes.
where you give it like a very simple prompt. You just say, you're a person who's suffering from anxiety, talk to the therapist. If I understood correctly from like skimming the top, the comparison is it's not just you have two different models that are prompted differently. It's also with the with what you've done, there's this interactive component where you chat and then you predict what the cognitive model is and you get some feedback on that. Am I understanding it right? That like the intervention is like that whole package of you talk to this, you know, more sophisticatedly prompted model, you get this feedback, you have this bit of an interactive process versus you're just practicing by chatting to vanilla prompted GPT-4. Is that right?
Yeah, exactly. So we can't provide, so the question is about the conditions for the mental health project. And yeah, so importantly, in the GPT-4 case, we don't have this ground truth cognitive model, so we can't really provide them with feedback. We just still ask them to do the prediction tasks, so that's the same, but we can't give them the feedback at the end. But yes, both of them involve interacting with the model, same instructions, and the conditions are just whether you get the feedback and also whether it was kind of programmed with the ground truth cognitive model and the conversation styles.
Got it. And then I guess I can ask more detailed questions when we chat, but a higher level question is, you know, in this setting, the outcome is really self-reported. You know, did you feel like this was a good training experience?
Yes.
And I think, you know, to previous points, it's like, how would you think about like longer term, you continue that work, like evaluating, like, does this work? Does this actually, you can imagine reasons why it might not. It might be the case that when you prompt with these cognitive models, it says, well, gee, my core belief is this, and therefore I blah, blah, it's like too easy, or, you know, it's not, there's many ways in which you could feel good about the training, but actually it's not really training you. And so how would you go about measuring that and exploring that more?
Yeah, that's a great question. So actually, that particular failure case is especially pertinent. So I think that you're right. The easiest way for these models, which have been RLHF'd into wanting to do what you want, is to just give you the answer that you're looking for. And that also means that trainees can start recognizing that and just say, hey, what's your core belief? Rather than trying to actually establish enough rapport with the patient for them to reveal it. So as future work, I think maybe having some sort of maybe explicit, let's say, like PGM or something that kind of dictates when the agent should actually reveal information based on rapport building would be really interesting. And looking kind of further out, I think doing some sort of actual like RCT in a classroom setting would be kind of the gold standard for actually being able to evaluate these models.
What sort of like outcome would you use? So the RCT setup makes sense. Like what's the endpoint? What are you measuring?
So I think, so first I'd like to maybe understand how these competencies, these various competencies are actually measured. So like if they take a quiz, then we can just have maybe pre-test quiz, interact with the model, post-test quiz to understand their maybe conceptual understanding. You might also want to be able to develop better, let's say, evaluation frameworks around maybe just the cognitive model construction. So I would say like that also requires kind of domain expertise and working with mental health professionals, which I'd be excited to do.
Makes sense.
So when it comes to interpretability, so in supervised learning, you have looked at many different things, like for example, features and in map and things like that. I guess when it comes to RL, I have a question like what is the biggest difference from supervised learning and what is the you talk about concept in state space, but maybe there's probably other things that just curious.
Yes, that's a good question. Let me see if I actually included those in my backup slides. So we looked at this in our kind of survey of interpretable or explainable reinforcement learning. I may not have included it, but the idea is there's a bunch of different ways in which you might want to be able to explain an agent's decision making. So and you can think of it most simply as like you can just translate supervised learning techniques from this like state to action mapping. So then at each decision point, you can get an explanation. Maybe that's a feature representation, maybe that's a heat map. But you can also think about the kind of like policy summary maybe as an explanation. Maybe you want to say, hey, what are you going to do in this environment? Or what did you do in this environment? And use that as an explanation. So that could look like a graph structure, that could look like maybe natural language summarizations. So I'd say that's one of the key differences, is this like temporal aspect in which attributes you want to include or make summary.
But do you explain every step? Because it's dynamic, there's the sequential, so it is temporal, you mentioned, right? That may make a bigger difference, but that do you explain every step, do you explain the?
Yeah, so going back to Russ's robotics example.
Yeah.
If you have this robot, it just keeps moving its actuators.
Yeah.
And you don't want to explain that, okay, here's why here's why I applied this force to this joint at this time.
Yes, so I think that, for example, in the concept setting, it's nice because maybe you can have the human construct concepts that describe the situation that they've been in. You might say like, you create this state.
Yeah, there is generally this bridge between a symbolic level of reasoning for planning an action, and then translating that into physical motion or action. And the challenge is often representational. How do I relate the symbols to the environment in a way that the machine can then do the action?
I see. So I guess in terms of like an explanation or interpretability setting, that also means like, how do I get a representation that not only enables AI decision making, but also maybe facilitates human decision making? And does there need to be an additional translation step in the process?
Uh-huh.
I think that's very interesting. I think in particular in robotics, this is maybe
Sure. This is something that in a lot of the kind of embodied intelligence applications that I'm interested in, a lot of those are surgical or medical, but I think are very interesting questions. By the way, Jason, are you the host?
I am.
Okay, Ramon has offered to give up his slot, or I could talk at 5.
Okay, can you send me an email? We'll sort it out.
Well, okay, I sent a thing to you. I'll send you an email.
Great, thanks.
I normally go to Mateus's group meeting between 4 and 5, but at 5 I could do something, or I could do 4:30.
Let's work out by email.
I will send. There's stuff in the chat from Raman, but I'll just send you and Raman an email, and you all can work it out.
That'll work.
Okay.
I'm leaving tomorrow, so if there's time, maybe tomorrow morning or something, I can
No,
also.
tomorrow morning.
We're working over it.
No, you don't see the calendars of people here right now.
No, I don't.
Okay.
I'm quite busy.
Anyhow, yeah, Jason, this is a very interesting seminar, and I should not monopolize the rest of the time. I'll quickly send you and Raman an email.
Cool. Yeah, thank you for the questions. I appreciate it.
Sure. Hey, Jason, if you reply, also text me because I'm going to be out and around. Okay.
Thank you.
Question over here?
Yeah, thanks for the great talk. You mentioned the applications of mental health, and I was wondering what's your clinical endpoint for this research line, especially applied to the mental health. Is it if there is one objective, then what would you like to optimize in this research line? For me, it could be like life expectancy, things like that.
Oh, I see. I think in this area of research, I think that my interest is to really address this bottleneck that we've uncovered in terms of actually enabling people to get care when they need it. So that's kind of to the goal of improving educational outcomes for mental health professionals. So I think that maybe a side effect of that is that there's increased mental health outcomes for individuals because they're able to actually access care. And then there's also maybe better training because these individuals are able to leverage new AI-powered tools to improve their own training to actually support people. So that's the kind of.
Yeah, thank you. Yeah, thank you. That is a good start. But how to measure it at scale?
Yes, I think that also speaks to this question earlier of like, how do you actually measure in the classroom? And I think that's really important. And I think like RCTs are the gold standard here. But I guess you're thinking more like long term, how do you at a societal level measure the kind of outcome of that?
Yeah.
I think that's hard. I don't know, maybe I know that you would find causality, so I feel like establishing like a causal link there might be challenging. But maybe there's some things you can do locally, like people, I don't know, enjoy their class more when you have this intervention. Do the individuals that those people help actually have better mental health outcomes, maybe like longitudinal studies. I'm not sure, but I think there's a lot of really interesting questions there that you're starting to touch on.
Okay, thank you.
Thank you.
Maybe I can follow up on a question Andrew asked before about, maybe it's even the same question, I'm not sure. The second column here on understanding and specifying goals. It's one thing about how that might, how humans might be able to help in situations where you would want hierarchical RL to work. So hierarchical RL never really works as far as I can make out. But it seems like with human guidance, for example, linguistic guidance, you could get some intermediate objectives.
Yeah, I agree. Yeah, so that's also my understanding. I did a bit of work on this in my undergrad in particular. And one of the main bottlenecks is like exactly how do you actually do this subtask decomposition? It's very hard to identify these subtasks. But if you have a human
Or maybe an LLM.
Or maybe an LLM, I guess going back to the example I gave to motivate the talk, we did get these like high-level subtasks from the LLM. So I think that could be a really exciting way to integrate LLM capabilities with RL sort of optimization power.
Yeah, so how would you go about doing it? I mean, you could think of reward shaping, you could think about actual hierarchical RL.
Yeah, so I think that in particular, I would want to maybe do some sort of, I guess, reward shaping approach where associated with each subtask is a particular reward that kind of describes that subtask. So you could ask an LLM to provide the natural language description, or you could use maybe code generation to actually define the particular reward function in code for that subtask. And then you can see if that works, but maybe you could also have a human refine, say the code has an error, and could use a human to actually correct that. That's how I would consider this.
Right, so that's a more complicated interface.
Yes.
For the human.
Much more complicated. So then again, probably some human-centered challenges to address there in terms of maybe you don't want the human to have to inspect all of the code that's generated. So how do you determine what the humans would actually interpret? Yeah.
Last question? Going once? Twice? Okay, let's thank Steph again for a great talk.
Wait, get 1 second before you end the talk. I need to get something off my screen.
us.
Oh, yeah. Okay, thank you, everybody.
Oh, God damn.
Yeah.
Well, then